Hello there, we're your peer grader. This is Kevin Bofsar narrating the happenings of lab number 1 for Physics 2211. Introduction. The purpose of the short demonstration in this lab is to analyze the motion of an object moving at a constant rate. As far as concepts goes, this experiment involves Newton's first two laws. Otherwise known as the principle of inertia, Newton's first law states that an object will continue its current motion until a force acts upon it. That is, an object at rest remains at rest, and an object in motion retains its current velocity indefinitely. The momentum principle is Newton's second law, and it posits that the rate of change of the momentum of an object is the net force, and the rate of change of the velocity is the acceleration. For this experiment, a video of the object moving was captured and its motion measured frame by frame using Tracker. In addition, a computational model was created in Python. Finally, both models of the position over time were compared. Unsurprisingly, we will find discrepancies between the two models. The simulated model maintains a perfectly flat rate of change, while the observed motion wanes in steepness. Experiment. The object observed in this experiment is a small car running along a track. After a momentary push, the car travels leftward on the track. 2 seconds of this leftward movement, starting from after the car is released, are captured and analyzed. Here, the system is just the car, as its motion is all that we're looking at. Conversely, the surroundings include the track it rides on and the entire rest of the universe. Observational model. Data points marking the displacement of the car at each frame of the video were constructed semi-automatically using Tracker. To do this, I calibrated virtual axes to define the x-axis as aligned with the movement in the video, as well as a measurement tool that used the established length of the car to define the distance it traveled throughout the video. Creating the points consisted of locating and clicking on the center of the car in the video frame for every frame of the video. For each frame, the program calculated the distance of the current center position from the origin I defined as the start. Computational model. The GlowScript code simulated the motion of the ball with a given initial position vector, initial velocity vector, and a force vector. Initial velocity was estimated to be and set to be the average velocity during the first 3 frames or first tenth of a second of the tracker data. The program was set to calculate data intervals at 0.033 seconds, or at a rate of 30 frames per second, as the video is recorded. Seen here, the program uses a position update and velocity update formulas derived from the relationships between position, velocity, momentum, and force in Newton's second law to recalculate the position and velocity of the ball at each time increment. Results. As seen by this graph, the 2 lines denoting position relative to time are mostly similar at the start, but diverge gradually by the end of the period. Decidedly, this is due to frictional forces, which were not considered by the idealized simulated model, but nevertheless exist and decelerate the car as it passes along, just as Newton's first law, the inertial principle, predicts. Since the forces in reality cannot be truly zero, and were not, the motion of the real object did not maintain indefinitely, like the computerized simulation projected. Error. For each frame in Tracker, there is a substantial chance for error in the precision with which the center of the car was located and clicked. Furthermore, the initial velocity inputted in the GlowScript model is nearly an estimate, derived from the start of the Tracker data, so it may yet be fundamentally inaccurate. What else? When the motion in the video was tracked, I assumed the positive x direction to be rightward, as is conventionally drawn. This means that the leftward position, and by extension velocity of my car, proceeded in the negative x direction. The directions totally could have been swapped, however the result would not have changed except visually. The rates of change would remain the same, but the graphs would travel upward rather than downward, effectively mirroring the results. The relationship between the observed and computational models would remain the same, and reflect the same discrepancy as previously mentioned, caused by the friction. The computational model functions with the net force equal to 0. However, this masks the total number of force vectors affecting the focal object. The force of gravity and the normal force by the track are easy to imagine, but there are many other smaller yet consequential interactions that occur between other factors in the surroundings of the car. Ergo, we cannot definitively list them all.